Okay. So here we are. We have about 85 people in our first meeting. So welcome to Organic Chemistry 1. I am Dr. David Irvin. My PhD is in organic chemistry. This is my chosen field. This is the thing I love. Okay. I love going to the lab. I love building things, making things. And the cool thing about that is that I've been doing this pretty long time, surprisingly. And I have about 10 to 12 years in academic experience. I have 10 years working for the government, including the Department of the Defense and Department of Department of Energy. And I also have about 12 years of industrial experience, including my last job where I built a $5 million machine that's now pumping out 1 million square foot of a polymer a year. So those are the different kind of aspects of it. And so one of the cool things about that is I have a different perspective on organic chemistry. I look for the practical side and how you can make it all make sense from a, ooh, how can I use this? How can I approach any chemical I've never seen before and try to figure out how it's going to react? And so I'm going to approach it from that particular way. So that being said, let me go ahead and start by sharing my screen and talk about how I will administer the course. Okay, so I'm going to share the screen right here. And the first thing I'm going to do is go to my track site. Canvas. Go to my Canvas site. So I think you should see the Canvas site set up here, right? Is that correct? Yes. Okay, so this is our section. I have 2 sections. This is luckily the 12:30 section and not the 8 a.m. because there's a lot more coffee drinking at the 8 a.m. section there. But so what you'll do is you'll go to the Canvas site, and under assignments, you will see that this is where you're going to go ahead and see all the, of course, once I start recording, there we go. This is where all of the assignments will show up as what to do that week, okay? You do not submit homework here, and you do not submit exams here. All you do is see when they're due, so they're on your radar, so you know they're there. The group activities will be submitting to Canvas on the day we actually do it, and I'll talk a little bit more about that. So let's go back to the home page here on Canvas. And I had a lot of trouble last time with trying to get everybody to, have the right, things due in the right place and know where everything is. So what I was able to do is I was able to create these buttons here, and these are active buttons for our class. And so if you just want to come to lecture right on time, you can click this button. It will take us directly to this class. Okay, so I think most of you probably done that. I don't see anybody actually emailing me that they can't find the link, so that's a good thing. All right, so then, as I said when I started the class, I'm going to record all these live lectures. Okay, so if you miss a class, don't understand, think your notes are a little bit fuzzy, go ahead and you can click on the video lectures, the lecture video here, and that's going to take you to YouTube. Okay, Canvas doesn't let me store videos to it. So what it does is it does allow me to go to YouTube. And so on this channel, this is just our channel for this class. And so it'll be just these lectures. And so if you miss something, go ahead. If you want to double check something, it's going to be found here. Okay, so there we go. So the next thing to look at is this book and homework, okay? The book and homework is on Top Hat. So it's an electronic version of the book. And according to Top Hat, you should have unlimited access to it for as long as you have access to Top Hat. So that's great. Some of the other stuff like exams and quizzes and stuff won't have access to, but you should have access to the book with that. So I'm going to click that and go ahead and go to Top Hat. Actually, I'm going to go back because I already have it open here. So in content. Well, maybe I should do this. There we go. So in Top Hat, what you should see is that there will be several assignments that are available to you. You're not going to see all the things you see on mine because I have a whole bunch of stuff like, exams and stuff like that. So you won't see any of that. And let's see, this is the class here. This is running a little slower than my internet at home, unfortunately. I think I'm going to try to hardwire it in next time. Okay, so what you should see once you start getting into this is there will be things that are highlighted, and those are things that are going to be assigned. And so there's things like homework, the book chapters, and there's also some slides that I will be presenting from. And if we look right here at Module 1, we have this right here, Module 1 reading is assigned right now. And what that means is that's the actual book, okay? And there are embedded questions inside the book that count as the homework, okay? So what you should do is go ahead and use this as your book and read through it and see what you have. And then what I think would be a good way to do this homework is to read through it and look at the question and try to answer it. If you get it wrong, it'll tell you got it wrong. You'll have 2 chances to do it. If you get it wrong, go back and read the section above it and see if you can get it right, okay? The other option is to go ahead and read through the book, come to the lecture, and then go back and try to do the homework at that time. That way you'll still have 2 chances to get it, but you'll be able to see if you understand it or not and use it as a probe to say, okay, I do understand this. I got it right the first time. I can move on to the next one, okay? And so we'll see that they'll have those questions embedded in here. For example, right here. This is going to be one of the questions that counts toward homework. And so the book and homework are all on Top Hat. Okay. Any questions about that?
So there's 2 attempts for the grade on the homework, the questions.
Correct. Yeah. So
Okay.
it's just it's just like on sapling or something where you just can't keep clicking on it until you get it right. So you get 2 attempts. Okay. So that's the book and the homework. And so what you'll see here is that you do not submit the homework on Canvas. The grades will show up in in Top Hat, and I will transfer them over about every 2 or 3 chapters. So that'll happen there. Will you get full credit for the second attempt? Yes, you will get full credit for the second attempt. So I have my chat up here on the side so I can see that. I have my participants here. Hey, we're up to 94 participants. That's great. Okay. All right. So then the next button is the activities button. And what you'll do here is we have 4 scheduled activities throughout the semester. These are going to be breakout sessions where you have small groups of 5 or 6 and you work through a set of problems together. Okay. So there'll be 4 of these, and then after everybody has turned it in, what we'll have is a live part of the class. I'll introduce the activity during class time. You'll have about 30 minutes in class time to do the activity, but it's not due until midnight of that day. So you can go and pretty it up or look for, let's say your group was just playing around, and so you can get some better answers by looking them up. And then turn that in, and then that is graded mostly on participation. So definitely come to these, do the participation, and turn these in. So it's a very good way to do that. Okay. And those will be highlighted here. This is the one thing you actually will turn in on Canvas. And so once I have those, I'm going to have those as electronic submission. You just upload an image or a PDF of the system, and that will get it where the activities go. Okay. So the next button here is the lecture and exam schedule. So I think this is correct now. I've just had to play around with it a little bit, but it tells you which modules we're going to do, when the group activities are. It even tells you when the homework's due. These should be aligned with the assignments under on the assignments tab too. So if they're not, go ahead and ping me and I will be able to correct that. Will these group activities occur during class time? And yes, the answer is they will occur during class time. However, you don't have to upload it until midnight that night. Okay, so the exams are on here, including the final exam. All exams are during class time and all exams will be taken on Top Hat. Okay, so I found it to be much easier to take exams on Top Hat than on Examity or other sites. I've had very few problems, and so hopefully that will work out really well for us. Okay, so the next button we have on our Canvas site is the syllabus, and so you can go and read that. And one of the key things in the syllabus here is if you started reading it a week ago, you'll see that the grading scale has changed. The SI they said I couldn't have SI be 9% of the grade. So I've changed the SI back to the 5% that's recommended. Okay, now we have what we call a supplemental instruction, which is a peer-led study group. Okay, and so what I would like to do is I'd like to introduce our SI leader for this class, Marcus. And he's a former student of mine. He was in my honors organic chemistry class 1 and 2. And so he really, knows a lot of this stuff, and he's really going to be a great peer mentor for you on this. So Marcus, can you go ahead and unmute and give us some information?
Hi class, I'm Marcus. Yeah, I was in Dr. Irvin's class. I received an A for his honors organic chemistry 1 class. Also did pretty well organic 2. I got a B, but we're going through a pandemic, so that's my excuse. But yeah, so I'm gonna go ahead and introduce the SI program and more about what I do as an SI and what the goal is. So I'm gonna go ahead and share my screen.
Okay.
Oh dang. Not the desktop. 1 second, y'all.
Technology is great.
I know, right? It's loading.
There we go.
Just trying to do full screen. Any questions about SI or anything? All right, so SI is basically like a weekly, it's like almost like a tutoring session. So basically everything you're gonna learn in class, I'm going to be doing, like going over, teaching you study skills, and basically trying to make the material easier for you to understand and learn. Relearn and focus and perform well on the exams. That's our goal here, is to perform well on the exams. This is a mandatory SI, so it is worth 5% of your grade. But it's not like, it's led by me. So come to my SIs, like, I know it's for a grade, obviously, but also come, it's gonna be fun. It's gonna be like really helpful for you as far as this class goes. It's not an easy class, so definitely participate in the SIs. But basically it's meant to be, a fun, informal way for us to be able to learn together and for me to be able to show y'all. And it's, y'all can see my screen, right? Okay. All right, so basically, why should you attend SIs, which is based off statistics? Students attend SIs on average receive a final grade, either half to a point higher than, or not a point, a whole letter grade higher than students that don't regularly attend SIs. And since this is a DFW class, which means DF or withdrawal has a high DFW rate. So most students who take this class do get a DF or withdrawal, and we don't want that for you guys. So this is why this high is mandatory. This is why, you know, I'm showing you these statistics, because it's recommended, especially for classes like this, that you come and, you know, get that grade up, because this is a hard class. All right. And the last thing is, I did send a survey link to everybody on Canvas. The survey will open, so that is just so that my SI schedule, my session times will fit with you guys' schedules. And I just need you guys to fill out that survey. It's available today. It's open for like 3 days. I just need you guys to fill it out so I can go ahead and get the schedule made and make sure that I'm available for all of you guys, and that everybody's gonna be able to attend enough sessions this semester to get the full credit worth of points. And I definitely I highly recommend you still continue to come to SIs even after the mandatory session period is over, because like I said, it is a good help for this class, because you know, this class. And that's all I really have to say, guys.
Hey, Marcus, when do SI sessions start?
And they start next week. So not on Wednesday. This week, like next week, so like Monday. Okay. So since your class is on Monday, my first session, have a look. My first session is Monday from 11 to 11:50. So next week.
Okay, I have a couple questions here in the chat here. Yes, the SI sessions are online. There will be Zoom links to it. The link is not currently active until 7 p.m. tonight. So you can't actually go until 7 p.m. tonight. You can get up to 2 sessions per week to get credit for it. However, it's best that you go to the same session every week so that we have the same number of people in all of the system. Okay? And the sessions are about 50 minutes. And of course, Marcus will have a kind of a lesson plan, some ideas on what to start with, and then of course be able to answer questions. And the more interactive you are in this, the more you'll be able to, you know, get a good, you know, extended knowledge on, you know, what Marcus has to offer in these SI sessions.
Yeah, I'll be sending out Zoom links closer to next week on the Canvas site to make sure everybody has, you know, the link to get into the Zoom meetings.
Yes, and there's another question. Yes, all SI sessions and all of my class are going to be virtual by Zoom.
Yes,
so we are going to be COVID safe here. Oh, I just got my COVID test back. I negative again, 3 times in a row. That's great. That's a good story. All right. So, a couple things about that. They start the week of January 24th, which is next week. To get full credit, you have to have all 10 sessions by April 11th. Okay. Now that is before finals, but there are 2 or 3 weeks after finals where we will be doing like final review sessions, and that's what we're going to focus on for those last ones. Okay. But you can only get credit for 2 sessions per week. So you can, if you miss a week, you can catch up, but don't try to go to the last 5 weeks, because that's not going to work. You really need to try to go every single week to keep up with the material. Okay.
You can't like go spaz on it. You can't like go to like 7 in 1 week or something, because I think there one is one available every day. So you can only get session for 2 out of that week towards your extra credit. But I mean, like, you know, if you want to go to 7 of them a week, I mean, you're gonna be ahead in the class. That's good for you, but so you know, you're not gonna get all the credit you need just by going to a lot at once.
Yeah. So and then in addition to that, I'm gonna set up what is it called? Virtual office hours, where I'll just be there answering questions. I actually will share that with this and the other class. I started doing this early on and nobody came ever. So, but we have enough people, I think, that I can actually have that for both classes at the same time. My other class is at 8 a.m., so it probably won't be at 8 a.m., but I'm going to try to set up a time probably on Tuesday or Thursday we can have some live office hours to get as many of you engaged as possible. Okay. All right. Thank you very much, Marcus.
No problem.
Okay. So let's go back to the Canvas site. Let's see, I have a question in the chat. It's if we went to 2 a week, would one session be one set of materials and the other session be the other materials? Maybe, but most of the time we try to focus on a particular lesson plan per week.
It depends how many chapters he goes over in the week. So like say Monday he went over chapter 3, and still on like Wednesday y'all are finishing up chapter 3, with the sessions for the whole week will be on chapter 3. Yeah. When we move forward until he move forward. So it's with the same pace of the class, not like lab all over the place and stuff. But
it tends to follow a little bit from, so I'll give the first lecture on it, and then the SI session tends to follow just behind that. So you've already heard it once in class. Okay. Okay, so that was the syllabus tab here on our thing. Then there's a resources tab. This resources tab is going to become great. In here, we have in this resources tab, I have a hot topics for each of the exams we have. All 3 exams have their own hot topic list here. They also have, in case you don't have Top Hat right now, you can actually download these PDF versions of the slides so you can keep ahead. And if you really like the PDF version of the slides, for example, when I take notes, I can actually use the PDF reader on my iPad and actually take annotated notes, and it saves them. And I think that's a really, if you like taking notes on a digital pad, that's one good way to do it. Okay. There's also, the lecture notes, but then there's also going to be the organic nomenclature review. This is a multi-page document, and we're going to start organic nomenclature on chapter 2. And so this is everything we're going to learn in chapter 2 is going to be in this resource. So that's what that slide is for. Let's see. Okay, I think all of those are answered. Yeah. And coming soon, I'm going to start recording videos this week, but there'll be a full videos session. This full video button will be operational next week. And what that is going to be is I'm going to break down each of these longer lectures here into a single topic. And it'll be like module 1, orbital shapes. Module 2, filling electrons, module 1.2, filling electrons, module 1.3, these Lewis dot structures. And so there'll be shorter videos. I'm going to target 5 to 7 minutes for these, and they'll start to appear on that channel. So let's say you're going along in your notes and everything looks good except for this one little thing. If it's that one little thing, you go to the full videos YouTube channel and look for exactly that topic to help you out. If that doesn't help you, go ahead and email me and we will talk about it. And we'll set up a Zoom office hours and talk about it then. Okay. So that's how best to use the Canvas site for keeping track of all your assignments and where they're due and what we're gonna, where everything's gonna be done. For studying, you all have a different study style, I'm sure. For me, I'm a very visual learner. So I like the idea that I can go to the book, click on a bunch of the different little videos and the activities, and then come to class and then watch the lecture and then be able to use my notes and then go and rewatch it in the video section. If you're more of a reader learner, the book itself is actually very eloquent and written by a couple of really cool Canadian guys. So it's actually very easy to read. And I think all of their additional information, the videos really help you visualize this a lot more than you would have in a static book. So I hope that you find that to be the case. Okay, are there any questions about the Canvas site or how the course is going to be structured? You can ask in the chat or live if you want. And we do have 99 participants in class. That is amazing. Okay. Okay, so what I'd like to do now is go ahead and move on to the next section, which is starting with our lecture. And the way I'm going to do that is Okay, so I'm going to go to Top Hat now. And so I have a question in the chat here about homework. So as you're reading the book, the reading assignment actually has questions built into it. Okay, so when you go to this question built into here, you're going to go ahead and click on it and answer it. And you have up to 2 chances to get it right to get full credit. Okay, so as you're reading the book, this is the homework. There's no additional homework here. And in this particular one, there's 46 questions in here, and it's going to be a total of 25 points, I believe, for each of these. I will fix that in a little bit. Okay. Oh, I did not share my screen, did I? Ha ha ha. Let me share my screen. All right. So can we see the shared screen now? Yeah, okay. Thank you. All right. Great. All right, so inside the reading assignment, this is the reading assignment, it'll say contains 46 items worth this many points. And notice it has responses here. This will actually tell you that you've answered those questions. And so it kind of tells you that you where you've gone. So let's see. So these are the homework questions. They're embedded in the reading assignment. So you don't have to go look for them separately. They're based on what you just read. It's a good way to probe whether you understood the material or not. Does that answer the question about homework? Okay, so the other thing I'm going to do is I'm actually going to try and see if I can present the internet's a little slower than I had hoped here. And what I'm going to do is when I present these live in class, I have to unassign them, but they are assigned for review of before and after class. And then during class, I can actually present slides from the Top Hat here. In addition to that, there'll be embedded questions as we move forward. And so what it's going to do is it's going to give you a code to do these questions. And so what I'll do is I'll actually go ahead and test out the take attendance. Attendance is not mandatory, but it's something I'm playing with and helping, if you're borderline, you might be able to do. Okay, so this is a way to take attendance. What you can do is only 58 of you seem to be in Top Hat already. So of course this won't count for or against you, but it's 2 ways to do it. You can hit join code or you can actually just text it, and these count for, and it'll keep track of that and tell me who attended and who not. And so what I can do is I can just minimize that at the end, and you'll see that there'll actually be a little a code on the top of the screen as I start presenting the slides. So I'm going to go ahead and start with our slide number 1, and let's see how that goes. Okay. Is it going to let me do it? 5, 4, 3, 2, 1. Next. There we go. All right. So these are exactly the same slides you're going to see on Top Hat. And what I'm going to do is I'm going to lecture through them and let you kind of, take notes in whatever way you want. And then so that we can learn the material. Now, all of the graphics are based on the book. So you'll be able to see those graphics again and be able to correlate them directly to the sections in the book. So that should be fairly straightforward to look at. So let me first talk about organic chemistry. Organic chemistry is one of those cool things because it revolves around carbon. And carbon is one of these things that has so many different ways that it can bond. It can bond with things like it. It can bond with metals. It can bond with other things. And so the variety in which it can do its bonding and the fact that it's so small and so prevalent makes it really vast in the number of different reactions we can do and the number of different organic compounds we can have. So what we're going to do first is we're going to, dive into a little bit of the general chemistry or the shape of the atom, et cetera. And then we're going to move into the more specific organic chemistry and organic chemical bonding. So the first thing we're going to do is we're going to look at electronic structure. And then we're going to look at that electronic structure and see how to predict the 3-dimensional shapes of molecules. And then after we look at those different molecular shapes and figure out how to do it, we're going to look at what kind of physical properties, such as boiling point, changes over time. So let's go to the next slide here. And there we go. Okay. So the first thing we have to think about when we think about bonding is, okay, what does bonding? Okay. So the cool thing is that all bonding is done by electrons. Okay. So let's talk about the nature of the electron and what it is. Okay. Let's see if it'll stop there. Okay. So it was learned long ago that we had kind of a paradox in the fact that we could either know where an electron was, or we could know how much energy it had. But you can't know both at the same time. And this is called the Heisenberg uncertainty principle. So this leads us to believe that, okay, electrons don't exist, you know, it's fake science. No, that's not true. They do exist, but they exist in such a way that it makes it difficult to first understand that the atomic orbitals are just a probability of where the electron will be 95% of the time over the course of a time regime. So if you think about it, so if you take 1 second and you say, where was that electron for, you know, from 0 seconds to 1 second, and it's going to be in that shape of that orbital 95% of the time. The rest of the time, it might be a little in or out of that orbital, but that's where it's going to be. So we have to think of orbitals as the probability of that electron being in that location over a length of time. Okay, that being said, we have different energy levels give us different sizes of these. And as we branch out into higher energy levels, we get different shapes on these. Okay, so the first energy level we have is just energy level 1. We only have one shape available to us, and that's the S, the spherical orbital. And the cool thing is we can put 2 electrons in any one orbital at most. Okay, so that means for every s orbital we have, an s, a 1s, a 2s, a 3s, we're only going to have 2 electrons in that orbital. Okay, so how can we do even more fun with bonding? Well, once we go from the energy level 1 to the energy level 2, we now still have an s orbital, but we've now generated a new kind of orbital called the p orbital. Okay, and we have 3 p orbitals of equal energy. Okay, so we have a px going on an x-axis, and it can have 2 electrons in it. A py going on a y-axis, and it can have 2 electrons in it. And then a pz going on the last axis we have, and that also has 2 electrons in it. Okay, which means in a p orbital of an energy level, you can have up to 6 electrons in it. Okay, now we don't use these very much in organic chemistry, but sulfur and phosphorus can put electrons into their d orbitals because they're bigger and have those available. And so I'd like to introduce the d orbitals as not being like the p orbitals in the fact that it has 3 equal energy levels. D orbitals actually end up having 5 equal energy levels, which means you can put a total of 10 electrons in a d orbital to fill it up. Okay, so a full s orbital is 2 electrons, a full p orbital is 6 electrons, and a full d orbital is 10 electrons. Okay, so how do we tell where the electrons are? Can we actually assign a location to individual electrons? And the answer is yes. This is the assignment. We can actually assign each electron a set of numbers that assigns it to one specific orbital, one specific location, and one specific energy and or spin. So let's talk about them. We have, the first thing is what we call our principal energy level. Okay, so we start, the nucleus is here, the first electron is out from it, and that's our first principal energy level. And then the next energy level is going to be 2, and the next is going to be 3, and the next is going to be 4. Okay, so that makes sense, right? So you're starting from the inside, going out, and those are different energy levels. Okay, so the next thing that defines that electron is the orbital shape. Okay, and these are defined with the systems of the n, or principal energy level, -1. So the first orbital shape we have is a 0, and that actually is the s orbital. You can think about a 0, looks like a sphere, s starts with a sphere, that's the way to think. So all of our 0 angular momentum numbers are spherical, or s orbitals. Once we go to the n of 2, now that we have the principal energy level 2, we can add the p orbital. So in principal energy level 2, we're going to have one s orbital and one p orbital, okay, because we've added that new orbital shape in that second one. We don't have any d's in that second energy level. Once we go up to 3 in the principal energy level, we now can have a third shape of orbital, which is the d. And then we can go on for the higher energy levels. But in organic chemistry, most of the time, we stay with just those first 2 or 3 energy levels. Okay, so that's the first 2 numbers, assigning any electron a GPS location within that atom. Okay. The next thing we need to look at is orbital direction, or the magnetic component of it. Okay, the magnetic component is whatever the angular moment is, plus or minus that number. So for example, in energy level 1, we only have one s orbital, which means our magnetic moment has to be 0, because it's 0 is for our s-shaped orbital. For 1, that means we have a p orbital. And remember, we had 3 p orbitals of equal energy. So that's going to be assigned -1, 0, and 1. Okay, that's how we get 3 orbitals, those 3 p orbitals, and they're all equal energy, because all we're looking at is the magnetic component, or think about it as orbital direction, the axis they're facing on. So a sphere has no axis, the p orbitals have 3 axes, and once we move up to the third principal energy level, that gives us d orbitals, and that would be a -2, a -1, a 0, a 1, a 2. So that gives us those 5 different shapes that we have in a d orbital. Okay, so the last thing we worry about is what we call spin. Okay, so electrons are negatively charged, and so they want to repel each other. Okay, however, electrons also have motion, and if you've studied physics, you have the motion of something with an electric field generates a magnetic field as it travels. Okay, so that means that an electron has a magnetic field on it, and so if you look at an electron, it's going to have a north pole and a south pole. Okay, now we can take that to our advantage by saying if the north pole is facing up, we have a +½ spin. If the north pole is facing down, we have a -½ spin. Okay, so those are the 4 numbers that'll uniquely assign every single electron in an atom. Okay, so what does this look like? Okay, so I like to look at it as an energy level as well. Let's space them out. And so energy is increasing as we go up the screen. So when we look at our first principal energy level, we only have that one s orbital. Okay, notice there's that 1 dash. That 1 dash means we can put 2 electrons in that orbital. Okay, so as we move up, we have the second principal energy level, which is the 2s and the 2p. Okay, right here. Okay, right here. Let me undo that. All right. So what that gives us is that we have them, and this is the second principal energy level. But it turns out once we start getting atoms close together, we actually separate the energy between the s and the p. They're slightly different in energy. So if we look over here, the s orbital in a multi-electron atom actually is lower in energy than the p orbital in that same principal energy level. Okay. Now notice that also happens when we go to our third principal energy level. The s's are below the energy of the p's are below the energy of the d. So what we can look at is visually, we have the lowest energy electrons are at the bottom of the screen. The highest energy electrons are going to be the ones that are going to be up here. Okay. So that being said, we must have a rule for filling electrons in the system. We're not just going to throw an electron up here somewhere because it is a very high energy level. Why wouldn't you start at the lowest energy level first? And that's what we do. So whenever we fill electrons into our orbitals, we start with the lowest energy level first, and then we move up. Okay. So we have a few rules associated for this orbital filling. First is you fill the lower energy levels first. Okay. So if you have 2 electrons and you want to put them in there, you're going to have to put them both in the first energy level before you populate that next energy level here. Okay, there we go. All right. So whenever we have this energy level, we have to fill that lowest energy level first. Okay. Think of it as nature is lazy. It wants to use as little energy as possible. And so it's going to be at that lower level. Okay. So the next rule we have for this is the idea that we are going to try to populate all of the orbitals of equal energy first. Okay, and that was what we do, we're calling maximizing total spin. So I told you that electrons have spin, right? And so we designate that in here by saying if the electron has a north pole facing up, it's got an upward arrow on its spin. Okay, so just like we started filling from the lowest energy up, we are now up to the 2p. We're going to actually want to put 3 electrons in those 3 individual orbitals before we start pairing orbitals up or before we start mixing our spins. Okay, so I said the ones that were faced up were +1/2. The ones that are facing down are -1/2. Okay, so you have 2 ups and 1 down, so 1 up and 1 down cancel each other out. So the spin is actually less than a total of 3 electrons. So we don't do that. We always want to have all the spins filling first. Okay, so we're filling the lowest energy first. We're filling all of the orbitals second. Now we can move on to our third rule. Okay, I need to minimize this slightly so that I can, yeah, there we go. Okay. Oh no. Yeah, there we go. Uh-oh. Where'd the slide go? Shared. No. Where'd it go? Oh no. Okay, let me select this. It's bogged down on me. I'm gonna have to actually present from home, I think. This is. Okay, I'm gonna stop share for a second, see if I can't get this up and running real quick. There we go. Present. There. I don't know, it bogged down on my side here. Let me. There we go. Present all. Start presentation. Oh, that's why. Okay. And I'm trying to get to the correct slide now. There it is. I did not know it does this. If you tried to do it midstream like this. Okay. All right. So we've talked about our filling rules. We fill from the lowest energy up. We fill all the equal energies where all our spins are aligned. And then we move on to our next rule. Our next rule is that If you have to put 2 electrons in an orbital, the only way they're going to do it is if their spins are opposite each other. Okay, and the reason is because you have both electrons have a negative charge, so they automatically repulse each other. Okay, but they're not actually occupying the exact same space in an orbital. However, when you have a north pole and a south pole of a magnet, they're attracted to each other. So that magnetic attraction decreases the amount of electron repulsion, and that allows 2 electrons to occupy an orbital if they are opposite spins. So whenever we have 2 electrons in an orbital, they must have opposite spins. One has an up spin and one has a down spin. Okay, so these are the rules on how we fill the orbitals. So how can we do this where we don't actually have to draw all the orbitals out? And so the way we do it is we look at the periodic table, okay? It's going to tell us. You don't have to memorize anything. You just have to understand that this is our number 1 principal energy level.
Dr. Irvin, you're not sharing your screen.
I'm not sharing my screen again. Oh, darn it. Thank you.
If you log into Top Hat, you can see him do the slides if you do the attendance code.
Oh, thank you.
Yeah, and it works better than if you share your screen on Zoom, because there's like no lag or anything.
Oh, really? That would be wonderful. Well, we'll try doing that when everybody has access to Top Hat, but for this one, we're going to muddle around with this. But that's a great idea. Thank you for that. I'm going to write that down. Watch live on Top Hat. That's going to be great. All right. So I should be sharing my screen now. There we go. Okay, so the way we're going to look at this, filling these electrons up, is we're going to look at the periodic table. And so if we look at this first row here is called row 1. That equates to our first principal energy level. Okay, so we have principal energy level 1, 2, 3. Okay, so what we can see from there is that we have a total of 2 electrons possible. So we put the first electron in this, and then we can put the second electron here. And that fills this orbital here. We're going to talk about those filled orbitals here in a little bit. If we go to our second electron principal energy level here, we have 2 electrons that we can put in these s orbitals, but now we have our first p's. Okay, and we have a total of 6 slots here that we can put electrons, because we have 3 orbitals that we can put 2 electrons in each. And if we go to the third principal energy level, we actually fill the p's first, but then we also can then fill the d's. That's why that third level is actually down 1, because it's still in that second energy level. However, it is going to be further down. And then if we go to our 4th and 5th and 6th, etc. But the idea is you're going to start filling electrons in this orbital first, then that one, and then this row is going to get full, and then this row is going to fill, and then this one. So we can take that same visualization and just apply it to the periodic table. Okay, let's see if did I click the button? Yes, all right. So how do we write this down so it's simpler, so we don't actually have to draw this out? So what we do is we assign our electrons by using this notation where we have the principal energy level is the first thing we see. The shape of the orbital is the second we see. And then how many electrons are in that orbital. Okay, so because S can only have 2 electrons, once we filled the first energy level in that S orbital with 2 electrons, we're done. We now have to put the next electrons in that second principal energy level. And the first orbital in that is, again, the S. And so we can put up to 2 electrons in that. And then if we still have more electrons to go, we can actually fill the next energy level here. Remember, we have 3 orbitals in P, so we can have a total of 6 electrons in P. Once we fill those orbitals, we go to the next principal energy level, which is the 3s. Okay, so what does that mean? That means that we have a nice way of differentiating the different types of electrons we have. Okay, when a orbital is full, they tend not to participate in bonding, okay? So we call those core electrons. Those electrons are under other electrons and do not interact with other neighboring atoms. However, the electrons that are in those unfilled outer shells here are called valence electrons, okay? Valence electrons are the electrons that do all the bonding, okay? So knowing how many valence electrons we have will tell us how many different things we will be able to bond to, okay? So let's talk a little bit more about valence electrons. Okay, valence electrons are found in the valence shell. The valence shell is the outermost occupied shell. Typically, it's not filled. If it was a filled shell, it'd be like a noble gas, okay? All the noble gases, heliums down to argon, all have a completely filled outer shell. And therefore, they don't bond. They don't have a reason to bond. They have a filled shell, okay? Now, if there's any electrons above or below those noble gases, those are called the valence shell electrons, and we can distinctly find the valence electrons by looking at the periodic table. For example, carbon will always have 4 valence electrons because where it appears on the periodic table. Nitrogen will have 5 valence electrons, and chlorine, fluorine, and iodine, bromine will all have 7 valence electrons. Okay, so do you have to remember this? No, you just need to look at the periodic table. It tells us everything we need to know. Now, older periodic tables have the group numbers. You have, this is 1A, 2A, 3A, 4A, 5A. So you'll see those. Those A numbers tell you exactly how many valence electrons are in there, okay? So that means hydrogen, lithium, and sodium all have 1 valence electron. Boron, aluminum, gallium all have 3 valence electrons. Carbon has 4, fluorine has 7. And of course, the noble gases are all filled shells, okay? So you don't have to remember anything, you just have to look at the periodic table. So that means that when we start building these structures and we have sulfur, we know that we have to put 6 electrons in sulfur to make it start bonding, okay? Or we have 5 electrons in nitrogen and phosphorus that we need to play with. All right, so now that we know how to find those valence electrons and we know that those valence electrons are the ones that bond, let's go ahead and talk a little bit more about, actually, oh, wow. I'm not going to use this today, but I'm going to have embedded questions like this in the future. I'm going to wait till we have more people who actually have access there. But this is what our embedded questions will look like. Once you're in there, all you'd have to do is, if you're watching online, all you have to do is click on which of these responses is correct. Okay, so sulfur we saw was in the group that should have 5 valence electrons. So all you need to do is look for the one, oh, there's none with 5 valence electrons. There's only 4. Okay, it's one of the ones with 4 valence electrons. So we'll see. So we have some people answering. We have 42 people signed up now. So what we'll do is we'll use this as a tool. And so then I will see the responses. And if people are, for variety of the class got, a majority of the class got it, then we can move on. If a majority of the class is still getting it wrong, maybe I should do that. So I just wanted to see if there. So you can also respond with your texting code as well. Oh, yeah, I'll explain that on the next slide. So let me explain the answer while we're playing with this right here. So I'm going to go back one slide. Okay, so when we have the core electrons, what we usually do is we look at the core electrons as the noble gas, okay? So if we look back at the periodic table here, it should be here. This is a lot more lag. I'm gonna have to present, okay, there it is. Okay. All right, so if we have our electronic structure, we know that By the time we get to neon here, we've completely filled our shell. By the time we get to argon, we completely fill our shell. So we can say that the electronic configuration of our core electrons is equal to that of neon. And then all we have to do is fill in the electrons we have left. So we have these two right here, which are going to be our 3s electrons. And we have 2 of those. So we'll have 3s2. And then we were doing phosphorus or sulfur. We were doing sulfur. So then we have to fill 4 electrons in that p orbital for a total of 6 valence electrons. Okay. So we have this, 2 of the valence electrons are from the 3s2, and the other electrons are from the 3p2 and 3p4. We have 4 electrons there. So the correct answer should be neon 3s2, 3p4, for a total of 6 valence electrons. I think I said it was 4. Sorry, I misspoke. All right. So I'm going to skip this question. So that would be the correct answer for there. Is there a specific periodic table you use? You can actually do this on any periodic table. If you know where the first 2 columns are and the last 5 columns, this trick will work on every periodic table. This particular one that is shown on the screen is the one that will appear on our exams. It's our departmental one, and it'll actually show up on the exams on top half. Okay, does that answer that question? All right. Okay, so now that we have the idea that the valence electrons are the one that do all the bonding, now we know how to find the valence electrons. We know anything that has a complete filled shell, those are core electrons, and only electrons above that do we care about bonding. Okay, so in organic chemistry, we don't have just one kind of bond. We actually have a continuum of bonds. The most extreme sides of it are the ionic bond, where it's purely ionic materials bonding, and they're only bound together by those opposite charges. And then we have on the other end of the continuum, the purely covalent bond, where everything is shared equally. Okay. Now, again, that's in a perfect world, and that doesn't really happen. So we need to talk about those 2 extremes, and then what some of the different places are in the middle. Okay, click the button. Yes. Okay, in ionic bonding, if we look at our valence electrons here, so sodium has its core electrons are below it here, and we have 1 electron in its 3s. If you look at the periodic table, it's on that first column, and it has 1 electron on that 3s. Okay. If we look at chlorine, it's on the end of that end, and so it only has 7 valence electrons, 2 in the s and 5 in the p. Okay, so neither one has a complete filled shell here. So they want to find a way to fill that shell. In ionic materials, it is easier for them to lose or gain an electron to fill a shell to be able to do this bonding. So in the case of this system, we actually have the sodium giving up its electron to the chlorine to have a filled shell. The chlorine now gains an electron and now has a filled shell. But in the process of losing an electron, we have fewer electrons than we have protons, and therefore we have a total +1 charge. Okay. In the case of chlorine, we now have 1 more electron than we have protons, and now we have a total negative charge. And so this is what we consider pure ionic bonding. The electron is going to be completely given away from one atom to the other, and they both have charges, and they typically both have filled outer shells. Okay. In contrast, we would look at other things. Okay. So how do we know if something's going to be ionic or covalent or somewhere in between? Okay. Well, we have to look at the electronegativity of the elements. Okay. And the electronegativity of the elements basically just tells you the desire for that element to have electrons. Okay. So if we look at our periodic table, fluorine is up on the top right-hand corner. It has the highest electronegativity of about 4 of any atom. So if you don't want to memorize numbers, memorize the trend that the fluorine is the highest. If we go way over here to rubidium, that's one of the lowest at below 1. Okay, so everything else kind of goes from there. Now notice that the electronegativity increases up the columns and across to the right on the rows. Okay, so as you move away from fluorine, the electronegativity drops. So we go from 4 to 3.5 to 3 to 5, 3 and 2.5. And hydrogen's a little bit special because it's closer right in between boron and carbon at 2.2. And then it goes down from there. Okay. So this difference in electronegativity tells us whether we're going to have a covalent bond or a different type of covalent bond or an ionic bond. The greater the difference, the more likely they are to form an ionic bond. Okay, so the rule of thumb is if the difference between those two atoms is 0 to 0.5 difference, you're going to form what we call a non-polar covalent bond. So each atom is going to donate 1 electron and it's going to share it equally. Okay, so neither one is going to pull that electron to either side because they both have about the same electronegativity, and we have a non-polar covalent bond. Okay, so they're completely sharing it. The step up from that is when we go from 0.5 to 2.0. This is where one of the atoms is more electronegative and therefore pulls some more of the electron density toward its side. Okay, when you pour more electron density toward your side, that gives you a polar bond. However, it's not big enough to be ionic. So we now have what we call a polar covalent bond. Now, what you'll see is the polar covalent bonds are the ones that do most of the reacting in our systems. And I'll try to draw your attention to that as we do. If the difference between those two atoms have electronegativity is greater than 2, they tend to be ionic. Okay, so you can even have covalent polar bonds between a metal and carbon if they're close enough together on the periodic table. And we'll see that when we start generating Grignard reagents in a chapter, what is it, chapter 9 or chapter 11? Excuse me. Okay, so what does that mean? What does polarity mean? Okay, so if we look at 2 atoms that have the same electronegativity, like fluorine, it's the highest, it's going to share those 2 electrons equally between them because they both have the same amount of pull on the electron density. And that gives us a non-polar bond, okay? However, if we do fluorine and hydrogen, which is just under the 2 mark, we have what we call a polar covalent bond. Now, when we have a polar covalent bond, one of those elements is more electronegative, it's in pulling that electronegativity to one side. So it's pulling electrons in this direction, okay? So what does that mean? Does it mean it's going to be an ion? No, but there is more electrons on that side, and so there's a partial negative charge, okay? That delta minus means there's a partial negative charge on that side, which means if we have something that's going to come in with a positive charge, it's going to hit this side of the bond because it's attracted to the negative, the partially negative side of this bond. Now notice this side, if the electron density is being pulled away from here, it becomes more electropositive and we have a partial positive charge. That means if we have a negatively charged species, it's going to want to attack this side of the bond. Okay, so knowing that bonds are polar and knowing which side is partially positive and partially negative will tell you something about its reactivity. Now, if you go from hydrogen to lithium, you've now stepped over that 2 mark and you're now in the 2.2 mark. And now you have a true ionic compound where the lithium holds a positive charge and the fluorine holds a negative charge, and they are electrostatically attracted together. Okay, so that being said, so now we have the valence electrons are doing the bonding, but the electronegativity of each atom is important to tell us what kind of bond it's going to do. Okay. All right, so now let's talk about covalent bonding and what it really means, okay? So each atom is bringing one electron, let's just say we're making a simple bond, one electron to the party, right? And so they each probably want to try to fill that shell such that they can have a full shell of electrons. But they can't steal the electron away from each other because one doesn't have a higher electronegativity than the other. So what do? They share those electrons, okay? So if you think about it, the two nuclei are going to be a certain distance apart, okay? And the electron from one is going to spend a little more time in between the two nuclei, and the electron from the other is going to spend a little more time in between those two nuclei. So those two electrons are electrostatically keeping those positive charges at a pretty fixed distance, okay? By counterbalancing the positive repulsion, having those two electrons in the middle kind of holds them there. And so as different nuclei at different sizes go, you'll see that length, that distance between them increases or decreases based on that nuclear size, okay? So in the case of them both being the exact same atom, they are shared equally. Those electrons are equidistant between those two, and we have a non-polar covalent bond. When we have two atoms of different electronegativities, those electrons are going to be slightly closer to the more electronegative atom, giving us our polar bond, covalent bond. All right, does that make sense? All right, so that being said, those electrons have to be in between those two nuclei more of the time. Again, remember that's where it's going to be 95% of the time, not where it is exactly all the time. So they're going to reside more time in between those. That is going to allow for those two positively charged nuclei to stay at that set distance. Okay, so why does it work? Well, it's saving energy, right? Each of your orbitals now has a total number of electrons to fill its shell. So it's happy, that's saving energy. And because they're shared between the two, neither one takes it, that's also saving energy, which gives a net stabilization to the overall system. So what does that net stabilization look like? Okay, so if we go on this far side here, let's say we have hydrogen and we're trying to jam them together by not having those electrons in between, and the two positive charges can actually see each other and try to repel each other. That's going to take energy. You got to squeeze those things together, okay? So if you start pulling them apart so they can't see, the two positive charges can't see each other until you get to a nice equilibrium where the positive charges and the negative charges are balanced out. Those positive charges really don't see each other. They're attracted to the electrons, and they have this nice stable distance between them, okay? That nice stable distance between them varies on the type of bond we have. So in this case, two hydrogens make a bond about 0.4 angstroms long. So as atoms get bigger, that distance gets bigger. As the nuclei have more positive charge, that distance gets bigger, but it'll always find that nice equilibrium distance. And that nice equilibrium distance is our lowest energy potential. Okay, so what does that mean? It means that when you measure a compound's bond length from here to here to here to here, you're actually measuring that lowest energy well where it's most stable. Now, as you try to take the distance a little bit further apart, they're going to start to interact less and less. They're going to share those electrons less and less. And so they're not stabilized by that energy. And at some point, they're going to be so far apart that they're not interacting at all. And so there's no energy associated with that at all. So the idea here is our driving force is we don't want to squeeze them too tight together. We want to have the electrons right in between those two, and they're going to find some equilibrium distance where they're going to be happy and covalently bound. Okay, what are we doing on time? Okay, I have 10 minutes left, I think. So we're going to move on to our valence bond theory. Okay, so this is basically, think about Lewis dot structures. This is where we're going to move on now. So we're going to look at the idea that all these elements either will gain electrons, lose electrons, or share electrons. And the driving force is to have that full valence shell. Okay. Now, all of the noble gases have 8 electrons in that valence shell, in that outer in that shell. So that derives it to what we call it the octet rule, which means all the main group elements should have a total of 4 valence orbitals, 1 s and 3 p. Okay. And then, so that means we have 2 electrons for the s, 6 electrons for the p, for a total of 8. So our target is, for most of the main group elements, we want to target 8 electrons in our system. I will be posting this on YouTube channel probably in a couple hours, because I'm on campus and it seems really slow. Okay, so what does that mean? Well, that means we want to follow a nice structured method to get us to a reasonable first approximation of what a structure might look like. Okay, so you can take any elements, throw them together, and by looking at their number of valence electrons and figuring out how many bonds they have, you can draw a reasonable structure to start with. Okay, and so what we call this is the method of drawing Lewis dot structures. And the first thing we start with is, how many valence electrons do each atom bring to the party? Okay, so if your molecule is neutral, all you have to do is add up all the electrons available, all the valence electrons available from all the atoms. Okay, however, if you know that the molecule you're building has charge, you have to account for that charge by either adding or subtracting electrons. If the molecule you're building is an anion, has a negative charge, you need to add at least 1 electron for each negative charge. Okay. If the compound you're building has a positive charge or more, you need to subtract 1 electron for each of those positive charges. So think about having a charged species is really what's the ratio of protons to electrons in all of the atoms available, and the deficit or excess gives you the number of charges you have. Okay, so let's do a few of these and just take a look and see if we can't figure some of these out. Well, gosh, we have, let's do this nice simple one here, H2CO. Okay, so if we look at our periodic table, we see we have hydrogen. It has 1 valence electron in its s orbital, and we have 2 of them. So that's a total of 2 electrons. Okay, we have 1 carbon, and if we look at it's on row 4a, which means it has 4 valence electrons. So we're going to write that down. And we have 1 oxygen. We have 6 valence electrons in oxygen. So that gives us a total number of electrons we need to locate on our Lewis dot structure is 12. Okay. And then I'm going to go ahead and do this charge species here. You can go ahead and do the other ones on your own to make sure you get the correct answer. But I'm going to focus on these 2 here during our lecture. Okay, so now that we know how many valence electrons we have available to us, well, that was actually answered already. I'm going to skip this question today so I can skip. Oh, there it is, skip. Come on, there we go. Because not everybody has access to Top Hat right now, I wanted to make sure that I don't take extra points for that. Come on. Definitely going to try to hardwire this. Okay, so now that we know how many electrons we need to spread around, let's figure out how to put them together. So the first thing you typically do is you put the atom with the lowest electronegativity in the center, unless it's hydrogen. Okay, hydrogen only ever bonds once, so it's never the center atom. Okay, so in the case of our compound here, just looking at the periodic table, oxygen is to the right of carbon. So we know carbon is our least electronegative atom. So we can put it in the middle. So we'll put carbon in the middle, and then we'll have to spread the others around. Okay. So the next step is, now that we figured out what our central atom is, we put the other elements around it and draw a bond to each of those other elements, okay? So we're gonna put our carbon in the middle, and we're gonna draw a bond to each of the other elements, okay? Now, here's the key thing. Each line represents a bond, and each bond represents 2 electrons, okay? Because they're shared. One's coming from one, one's coming from the other, and they're being shared. So when we count the number of electrons we've already represented here, in this particular case here, this represents a total of 6 electrons, okay? All group 2 elements will never exceed the octet rule, okay? However, sulfur and phosphorus right here, the group 3 elements can, okay? They can because they have these d orbitals available to it, and you can have around 6 bonds, around 6 electrons around there. But for the most part, when we're talking about carbon, nitrogen, hydrogen, oxygen, we are only going to have 8 electrons available to us. Okay, so the next rule is, now that we've drawn bonds between each of the things, now we have to sprinkle the remaining electrons in the system, okay? So in the case of our H2CO, we had a total of 12 electrons we had to play with, right? So we have 1, 2 for this bond. We have 1, 2 for this bond, 1, 2 for this bond. So that means we have a total of 6 electrons. So it means we have to put 6 more electrons in our Lewis dot structure, okay? So we're gonna put those on the most electronegative atom, okay? Oxygen is our most electronegative atom, so we're gonna sprinkle those electrons around the oxygen. Why? It has the highest electronegativity. It's the one that wants the electrons. So we're gonna put the electrons on that more electronegative atom first, okay? Now, are we done? No, because now we have to make sure all of our elements, especially our group 2 elements, have 8 electrons around them, okay? So in the case of all of these, we actually can have weird odd numbers of electrons in these systems. And in the case here, we have really nicely evenly spread out over all of the atoms. Okay, so our next step is to make sure each atom has 8 electrons on it, okay? So, I'm sorry, I skipped step 5. Step 5 is, once you've put all of the electrons around, you have to think of them as whether we have an odd number or an even number of electrons, okay? If you have an even number of electrons, you always represent them as pairs, okay? So they're always going to be in pairs. If you have an odd number of electrons, that means you can have 1 single electron out there by itself, okay? Typically, these are what we call non-bonding electrons because they're not the ones that are the lines in between the atoms, okay? And again, once we start doing that, we cannot have more than 8 electrons around any row 2 element. And typically we don't have any more than 12 in a row 3 element, sulfur and phosphorus. And that moves us to our step 6. Our step 6 is, let's make sure all of our atoms have an octet, or our central atom has an octet. So in the case of carbon here, we have 1, 2, 3, 4, 5, 6 electrons. We do not have an octet. So the easiest way for us to get an octet is to use the 2 electrons that we added to the oxygen here to generate a second bond with carbon to generate its octet. Now let's look at this. We now have a total of 4 bonds, and remember each bond is 2 electrons, so we have 8 electrons around carbon. But what happened to oxygen? Okay, well come on, there we go. If we look at oxygen, it's still sharing these 2 bonds, but it has 2 lone pairs. So it has 1, 2, 3, 4 in lone pairs, but it also has 4 electrons here. Oxygen has 8 electrons around it. So once all of our atoms have 8 electrons around them, if they're not hydrogen, then we have a valid Lewis dot structure. Notice when we do that here, we end up with having to move just 1 set of electrons to gain 8 electrons around nitrogen. But these 2 oxygens with single bonds still have 8 electrons. So you can use this lone pair to make a second bond with a neighboring atom to generate that octet for each of the atoms. 1, 2, 3, 4, 5, 6, 7. Notice we don't have an octet here, but we ran out of electrons. So we have to leave that unpaired electron there. Okay. And we're out of time right here. The next thing we're going to do is formal charge. Now, once we have a valid structure here, we're going to figure out if there's a charge on one of the elements or not. Okay. So your time is valuable, and I had a couple of glitches, so I would have normally gotten through this slide. I'm going to go ahead and stop sharing and stop recording. And if you want to